This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover the basics of acids and bases, so we'll start with the two definitions that you need to know, and then go over some essential equations. There are two definitions of acids and bases that you need to be aware of for the test. The first one is the Bronsted-Lowry definition, and a Bronsted-Lowry acid donates a proton, and a Bronsted-Lowry base accepts a proton. Look for the transfer of a hydrogen. So in this equation, we're going to see how a hydrogen gets transferred. And remember that a hydrogen is just one proton and one electron. And when the hydrogen gets transferred, it doesn't take any electrons with it. So that's why we say it's just the transfer of a proton. So in this chemical equation, we have molecule A and molecule B. And molecule A is attached to that hydrogen or that proton, and it gets transferred to molecule B. So then on the right side, we can see that the proton is attached to B and A has lost the proton. So that would make B the base, HA is the acid, and then after a Bronsted-Lowry acid loses a proton, it's called a conjugate base. So then A minus on this side is the conjugate base. And then after a Bronsted-Lowry base gains a hydrogen or a proton, then it's called the conjugate acid. So then this is the conjugate acid, the BH. The second definition is the Lewis definition. And a Lewis acid accepts electrons and a Lewis base donates electrons. So it's a pretty different way of looking at this. And here we have an example on our second line. And in this example, the fluoride ion is attacking the BF3. So the bond that's in that BF4, this bond here, that was formed from this lone pair of electrons. So the electron donor was the fluoride ion, which makes that the Lewis base, and then the electron acceptor was the BF3, so that makes that the Lewis acid. So to identify Lewis acids and bases, you'll have to be thinking about the structures of molecules and thinking about where did the electrons come from that form the new bonds. And whatever molecule is donating those electrons, that's going to be your base. Whatever accepts it, that's going to be your acid. And so if you think back to what you know about organic chemistry, the Lewis base corresponds extremely well or pretty much one-to-one with the definition of a nucleophile. And then a Lewis acid would be the same thing as an electrophile, which we'll talk more about those two things in organic chemistry videos. In this last example, we can apply both definitions. So if we go with the Bronsted-Lowry definition, we can see that our first molecule here, which is an ammonia molecule, is accepting this hydrogen. So that would make it a Bronsted-Lowry base. But at the same time, if we go with the Lewis definition, it's donating those electrons to the hydrogen. So that makes it a Lewis base. So it's both a Bronsted-Lowry base and a Lewis base. And that would make the hydrogen a Lewis acid. And additionally, if you look on the right side of the equation and you think about the reverse reaction, in the reverse reaction, this molecule, the ammonium ion, is losing a hydrogen, so that would make it a Bronsted-Lowry acid. When we talk about the strength of an acid or base, we're pretty much just using the Bronsted-Lowry definition. So we're only talking about the ability to gain or lose a proton. The strength of an acid or base is given to us from this value that is Ka or Kb. Ka is an equilibrium constant for this reaction here on the left. And what that reaction is an acid, a Bronsted-Lowry acid, donating its proton to water and then creating this ion here, which is called a hydronium ion, and then the conjugate base, which is A minus. And that makes water the base in this reaction. Ka is an equilibrium constant, and all equilibrium constants are equal to products over reactants. So for this one, Ka is equal to A minus times the concentration of the hydronium ions over the concentration of HA. So it's just products over reactants, but we're leaving out water because in all equilibrium constant equations, pure liquids and pure solids are left out. The number for Ka is dependent on the acid itself. So what the Ka tells us is if we put that particular acid into water, how much is it going to donate its hydrogens to water to create the hydronium ions? So the higher the Ka, the more hydrogens were donated, which means a stronger acid. So as Ka goes up, acidity also goes up because the concentration of hydronium ions are going up. Another way that the strength of an acid can be represented is by this equation right here, and with another Ka that corresponds to products over reactants for this equation on the left. What this equation is showing is the dissociation of the hydrogen from the conjugate base. In reality, the H plus ions are going to combine with water and always form the hydronium ion, like what we saw in the first reaction. But for whatever reason, it's way more common for H plus ions to be used whenever we're talking about acidity and the pH of solutions. So the big takeaway here is that either one of these equations are perfectly valid to use when you're talking about the Ka of an acid or the strength of an acid. And you need to understand that those two terms, H3O and H+, can be used completely interchangeably. On the right side, we have the equation that shows us the strength of a base. And remember, we said that bases accept hydrogens. So in this reaction, we have B representing a base taking a hydrogen from water. So we're measuring this by putting a base in water and seeing how much does it take hydrogens from water. And then that creates our conjugate acid and then these hydroxide ions. Kb is the equilibrium constant for bases, and again, it's products over reactants. And what it's showing you is how likely is that base to take the hydrogen from water. So the higher the Kb, the more likely that base is to take the hydrogen, so the stronger the base is. And the more basic something is, the more it's going to increase the OH concentration. The other way that you can see bases represented would apply to situations where you have a base that's a cation that's combined to the OH anion. And that's what this BOH is right here. So the base would be a cation. And what this version is representing is when molecules like this dissociate into the individual cation and then hydroxide anion. So your Kb for this one is a little bit different than the one above, but it's still just products over reactants. And the higher the Kb is for this one, the more OH gets produced. So once again, as the Kb goes up, the basicity goes up and the hydroxide concentration would go up. Let's look back on the left side to discuss pKa. Ka and Kb are going to have a huge range of values depending on the acid or base. So they could range from something like 1 times 10 to the negative 7 for one particular acid, and then for another acid it could be something like 3 times 10 to the 5. So, and that's not even the complete range. It can be even wider ranges than that. But the point is that Ka can be really huge numbers. So what we do to give us smaller numbers to work with is we take the Ka, we put it into this negative log equation, and it gives us the pKa, which is just going to be a much smaller number to work with. We'll look much more about how you solve logs in a video about MCAT math, but what you want to do whenever you're solving a log is apply this approach right here, where whatever is inside of the parentheses, so Ka or x, will end up being on the right side of the equation here, and then whatever your log equals, so y, you're going to take 10 and raise it to the power of y. So 10 to the power of y equals x. What you end up getting, if you were to plug in a couple numbers and play around with that equation, is that as Ka goes up, the pKa goes down. So lower pKa means a stronger acid because a higher Ka means a stronger acid. And then the exact same stuff would apply whenever you're trying to find the pKb. pH and pOH are some of the most important concepts when you're talking about acidity. And what the pH is a way for us to take the hydrogen concentration, which is going to be very large values, and then get it to become a much smaller value represented by pH. So it's the exact same equation and the exact same reasoning that we use when talking about going from Ka to pKa. And you need to have this very well memorized that as the H plus concentration goes up, the acidity of the solution goes up. And again, we'll look more at this math in future videos, but if you plug some numbers in here and work with this equation for a couple of them, you'll see that as H plus concentration goes up, the pH decreases. So let's do one problem right now and see how you can solve this. So what is the pH of a solution with an H plus concentration of 1 times 10 to the negative 4? So you do pH equals negative log of 1 times 10 to the negative 4. Now look at this format here to see how you need to solve this. The first thing we want to do is get that negative sign on the other side of the equal sign. So we have negative pH equals log of 1 times 10 to the negative 4. And then now we just take the approach that we have written on the left. We take 10 to whatever is on the other side of the equal sign. So 10 to the negative pH equals whatever was on the inside of the parentheses, which is 1 times 10 to the negative 4. And 1 times 10 to the negative 4 is the same thing as just 10 to the negative 4. So we have 10 to the negative pH equals 10 to the negative 4. So then if pH were just equal to 4, that would give us our answer. So pH is equal to 4 in this problem. You can do the exact same thing with the OH concentration, and the thinking is the exact same. All you need to know is that as OH concentration increases, the acidity decreases. And then the rest is the exact same. So if the pOH decreases, that means that the OH minus concentration is increasing. The last thing we'll look at is the auto-ionization of water. And this is a super important concept because it helps you understand a ton of relationships that are going to be really important for your calculations when dealing with acids and bases. And it all revolves around this equation here. And this equation shows us that some amount of water is going to ionize into H plus and OH minus ions. And we do have an equilibrium constant for this, which is Kw, and Kw is always equal to 1 times 10 to the negative 14. So since Kw is equal to H plus times OH minus, then those two concentrations multiplied together is always equal to 1 times 10 to the negative 14, which is super useful because that means if you ever have one of these values, then you can calculate the other value by using that number. And then we're not going to look at the proof for this, but it also leads to this being true, where the pH plus the pOH equals 14. So once again, if you have one of those values, you can find the other. So if you start with the OH, the H plus concentration, the pH, or the pOH, if you only have one of those, you can find all three of the other. And to go from pH or pOH back to the H plus or the OH minus, you would do 10 to the negative pH equals the H plus concentration. And then if it was the OH, you would do the opposite to find the hydroxide concentration. And then same thing with the pKb earlier, or the pKa. If you did 10 to the negative pKa, you would get the Ka. So all those equations are super important because it helps you take one value and get tons of other values from it. The last thing we want to look at is looking at our examples that we used earlier of the NH4 donating a hydrogen to H2O. So this is the acidic reaction on the left. And then we are looking at the conjugate base reaction on the right with NH3, which was the conjugate base. And on the right side, NH3 is taking the proton from the H2O. So what this is the Ka for an acid, and then we have the Kb for the conjugate base of that acid. So if you ever take the Ka of an acid, multiply it by the Kb of its conjugate base, that will equal the Kw. And so again, we can use the Kw to allow us to go from one value, whether we have Kb or maybe we have Ka, and then we can find the other value because we know that Kw is always equal to 1 times 10 to the negative 14. And then that also makes this true at the bottom, where the pKa plus the pKb equals 14. And again, don't worry about the proof of any of these. Just have these equations memorized because it helps you become way more fluid when you're solving acid-base problems.